Hello, everyone. Thank you for joining this webinar today. I'm pleased to be with Dr. Miaomiao Zhang and Dr. Soroush Mahjoubi to talk about an array of solutions that we can implement to improve the efficiency of the concrete production in general, particularly those areas that we haven't looked into in details, but throughout this research and implementation cases, we realize that they have a substantial role towards decarbonization and resource efficiency. To start this presentation, I would like to bring the role of project stakeholders, particularly the construction project stakeholders, in achieving a lower carbon cement and concrete to your attention. When we think about the array of solutions and stakeholders, starting from the left figure, clinker and cement production, we see that cement producers, fuel and feedstock providers playing major roles, and they have direct influence on the resource efficiency and decarbonization. Obviously, a regulator and policymakers play a major role in all the value chain and in all the project steps. But moving on to the concrete, we have concrete producers involved. And once we are going out of the concrete plant gate, particularly at the construction stage, we see that the number of stakeholders increase significantly. For example, testing agencies, architects, contractors, owners, and designers, they all have important influence on the decarbonization and resource efficiency. Our today's presentation is around the role of these three important stakeholders: testing agencies, concrete producers, and contractors, and how they can help decarbonize the concrete operational GHG emissions and obviously improve the resource efficiency. And the solutions that we are going to discuss with you is one, shifting from prescriptive specifications to performance-based specification. What's the carbon implications and resource efficiency improvements as a result of that? Second is about the impact of over-design beyond what codes require us to do. And the third one is the impact of testing quality and variation in the test results and the amount of over-design that is induced only by testing variations as well. Without further ado, I'm going to hand this over to Soroush to talk about the testing variations and over-design and its carbon and resource efficiency implications. Soroush, please take it away.
This part of the webinar is about the potential impacts of over-design and the strength variability on the life cycle carbon emissions of concrete. So let's start by understanding how over-design contributes to greenhouse gas emissions and costs in ready-mix concrete. Over-design occurs when concrete is produced stronger than the specified strength, creating a safety margin for strength compliance. And while this ensures quality control, it has significant environmental and economic implications. As we increase over-design, we need more binder and cement, which directly translates to higher GHG emissions and costs. And this diagram shows two concrete mixes, Mix A and Mix B, where Mix B has greater over-design than Mix A, represented by orange markers O1 and O2, showing the relationship between the over-design levels and environmental impact. Now let's examine the quantitative impact of over-design across different strength classes. We define over-design as how much the observed average strength exceeds the specified strength using the formula shown here. And this violin plot shows the distribution for a 2000 PSI mix where the average over-design exceeds 50%, with the 95th percentile reaching about 120%, and the median sits around 50%. And our analysis reveals pattern here, and lower strength mixes carry the highest over-design, with some exceeding their specified strength by up to 150%. But for the higher strength mixes above 6000 PSI, the average over-design drops to less than 25%. And this is because the higher strength mixes are more expensive to produce for the ready-mix mix companies, and achieving a strength beyond the specification is already more costly for these productions. Okay, now we investigated the over-design compared to the ACI safety margin, and our study shows that over 90% of mixture codes exceed the conservative ACI safety margins. These violin plots show the distributions of observed compressive strength, the ones that we found using experimental tests, across different specified strength levels. And the green and blue lines represents the minimum required average strength without sufficient historical data according to ACI 318, and these thresholds are actually conservative thresholds, and it is logical that the mixed codes lay inside the green space that is shown in this figure, but we can see that most of the strength average strengths consistently fall well above these conservative thresholds, and this suggests that there is a significant room for over-design optimization without compromising the safety, which could lead to substantial reduction in carbon emissions and costs. Beyond over-design itself, a strength variability plays a crucial role in over-design and driving the carbon emissions and costs. So the variations in strength indirectly increase the over-design because the producers must maintain a safety margin to ensure the compliance again. And here we can see that the diagram shows two mixes with different variability levels, mix A prime and mix B prime, where V1 and V2, which are the average strength, and V1 is less than V2, representing the lower and higher variability respectively, and strength variations arise from, and we can say that like the variability arises from four different sources: batching variations in material proportions, material property variations like cement reactivity, SCM reactivity, aggregate size and shapes and properties, and operational variations in mixing and handling, as well as the environmental factors such as temperature. Just as we saw with the over-design, lower strength mixes also exhibit the highest strength variability. We quantify this using the coefficient of variations, which is the standard deviations divided by the average experimental strength. And these volume plots shows the coefficient of variations, and it demonstrates that the variability decreases as the specified strength increases. And for 2000 psi mixes, the average coefficient of variation is around 13%, with some batches showing variability as high as the 80%. And these extreme batch-to-batch variations across mixture codes create significant quality control challenges. But in contrast, for mixes above 4000 psi, the average coefficient of variation typically drops below 10%. And this is primarily because of the better quality control in these more costly productions. We have also investigated the impact of laboratory test variations on the strength over design and variations, and we could see that the external laboratory testing introduces another critical source of variability that significantly impacts the concrete strength compliance and risks, and this is a part of the operational variations. And our analysis shows that internal labs report a coefficient of variation of around 6%, while for external labs can reach up to 13% for this specific mix code due to inconsistency in sampling, handling, and testing procedures. And we can see that the higher variability directly translates to increased non-compliance rates with external labs showing failure rates of 3.6% and 4.5% compared to internal labs. And these non-compliance risks create substantial business impacts, including costly rework and project delays. And the coefficient of variations also across different labs is different, as well, as you can see in the blue lines in this figure. Okay, so to quantify the carbon impact of overdesign, we developed a comprehensive data-driven modeling approach using the batch-level operational data. This figure shows the fundamental relationship between the carbon emissions, mixed proportions, and observed strength. And this is how the mixed proportions relate to observed strength and performance. And we see on the right-hand side that our integrated modeling framework that combines real industry practice data with regression analysis to create a data-driven model to basically connect the observed strength with carbon emissions. And by using the actual batch level operational data, we can capture the true environmental impact of current industry practices and overdesign. Okay. So here we have developed a simple symbolic regression model to establish a relationship between mixed proportions and GHG emissions. In the left-hand side, you can see the goodness of fitness for this model, and the root mean square error for this is about 7 kilogram CO2 per cubic meter. And in the right-hand side, these figures represents the relationship between the 28-day strength, which are the observed ones, versus the cement clinker SCM percentage and admixtures dosages. And each line color represents a company. As you can see here, each company has its own strategy in strength gain. And we use the linear regression model here to input to the symbolic regression model. And at the end, we could be able to relate the overdesign and strength variability to the excess carbon emissions. So in these two plots, I'm showing the overdesign percentage and coefficient of variations with the excess GHG emissions of different strength, specified strengths. And we can see that by increasing the overdesign, the carbon emissions increases linearly, but the impact of overdesign increases by increasing the specified strength. And in the right-hand side, we considered 99% compliance with a z-score of 98%. And we use the ACI formula to relate the strength variations to the overdesign here. And we found that, again, the coefficient of variations has a significant impact on the carbon emissions, and the relationship is non-linear. And for higher strength mixes, the impact is more significant, and it can induce carbon emissions up to 200 kilogram per cubic meter for high strength mixes. Here, we developed a overdesign versus coefficient of variation space, and we wanted to show the excess carbon emissions in this space, and each dot represents a mixed code in industry, and we have compared the average overdesign coefficient of variation with 99% compliance according to ACI, and no excess overdesign. So for 4000 psi here, we can see that there is a gap between the average and no excess over design dot that represents no capex opportunity to reduce the over design, but keep the safe margin up to 99% and compliance. And there is another opportunity here is that we can actually reduce the coefficient of variation and reduce the over design together to achieve higher GHG gains. And we consider 3.5% coefficient variations here to just show that we can have higher GHG gains by doing that. Okay, the next part of this presentation is about the impact of different variations, different input variations, such as the materials, batching, plant variations on the strength of concrete. And we use an interpretable AI method called SHAP to basically get some insights from the predictions of the machinery model. As you can see in the black box predictions, we have a complex machinery model, and we are not be able to understand the decision of this machinery model. But with SHAP framework, we can actually get some insights and find out the contribution of each feature to a prediction. So by using the SHAP model, we could identify the influencing factors. So in the left-hand side, this is the goodness of fitness for the machinery model gradient boosting machine that predicts the observed 28-day strength based on the mixed proportions, physical, chemical properties, and operational conditions. We considered the ready-mix plant, laboratory, and projects here as the input variables for this machinery model, and there are over 30 different input features here, and I've shown you only 5 of them in the right-hand side, and that has the highest influence on the predictions. So we found that cement clinker, for example, has the highest impact on the compressive strength and limestone content, etc. So these are the intrinsic features that we have considered. But we have also considered the operational features, as I mentioned, such as the ready-mix plants, laboratory, and projects. And these variables has a significant influence on the predictions as well. For example, the ready-mix plant can increase or decrease the compressive strength by over 1000 psi, and this shows the variations in handling and mixing in the ready-mix plants. And by standardizing these procedures, we can actually have some GHG gains, and we can reduce the GHG by improving the quality control in the ready-mix plants. The same applies to the laboratories. We can see that the laboratories have an impact on the laboratory has an impact on the compressive strength too, and this leads to a reduction or improvement in the compressive strength. We were able to also find out and quantify the impact of plant projects, temperature, and materials variations on mix codes. So we considered the 5% quantile, which represents one of the worst case scenario for the quality of operations, and 95% quantile represents the best quality of operations. And we could see that these variations has an impact on the 28-day strength too. So by reducing the material variability, plant-specific practices, and temperature control, we can increase the strength by 5 to 50%. And this impact is higher for lower strength mixes. As you can see here, for example, for 2000 psi, we can improve the average 28D strength by removing these variabilities. We could also be able to decompose the coefficient of variations using the SHAP explainer, and we found that we can basically categorize these variables into batching, materials, operations, and environmental conditions. And we found that the batching variation is the dominant source of variability and can explain about 40 to 50% of strength variations within the mixed codes, and material-related variations also explains about 40% of the variations in the mixed codes, and the rest goes to the operational variations, which is about 5 to 20%. At the end, we have translated these variations into GHG savings, and we found that by removing the batching, material, operational, and environmental variations, we can reduce the GHG emissions by 10%, 10%, and 5% respectively. And in total, the GHG reduction potential is about 25% on average for different specified strength mixes. At the end of this study, we have translated the GHG savings for each state within the United States, and we have also calculated the cost savings based on the average cost of mixed codes in the industry. And we found that by removing the overdesign, by optimizing the overdesign and removing the batching, operational, and material-related variations, we can annually reduce the GHG emissions and costs by 10,000 kilotons and $2 billion. And these savings are higher for Texas and California, as well as Florida, because of the supply of concrete, ready-mix concrete. Here are the takeaways from this study. Overdesign is significant. Excess overdesign is significant in industrial mixes, and 92% of the mixes overshoot ACI targets. And the variability sources were studied here, and intrinsic batching variations and plant and lab variations each explain 40% of strength variations in average, and this is one of the top tier decarbonization lever, and we can potentially reduce the GHG emissions by 25% by overdesign optimization. And here are the recommendations from this study. By reducing the within batch variations and batch-to-batch variations, we could lead to carbon savings. We can consider precise strength testing, use proper sampling techniques, and maintain consistent material handling to improve the within batch quality and variations. And we can also reduce the batch-to-batch variations by ensuring the uniform quality and proportions of ingredients, and control the butter to cementitious materials ratio, and avoid retempering. And in the training and education side, we can conduct regular technicians training programs, provide comprehensive instructions for end users, and we can also utilize automated systems for real-time monitoring and concrete manufacturing in ready-mix concrete facilities. And at the end, we can encourage testing agencies to upgrade testing facilities for better precision and accuracy.
All right. Thank you very much, Soroush, for this presentation. We are going to hand this over to Dr. Miaomiao Zhang, who will tell us about the research on prescriptive specifications and how eliminating and relaxing them would help us improve the resource efficiency. In the meantime, I would like to invite everyone to post their question in the chat box, so we'll be able to have a Q&A at the end with the speakers as well. Miaomiao, please take it away.
Okay. Hi, everyone. My name is Miaomiao Zhang, and I'm going to talk about identifying lower carbon concrete mixture through spec-aware JJ modeling. And first, we need to understand what is the concrete prescriptive specifications. They are detailed requirements set by governing bodies, such as State Department of Transportation, state DOTs, that mandate the specific concrete mix compositions. These specifications often include parameters such as maximum supplementary cementitious material limitations, SCM, the upper limit of SCM content, such as flash or slag, the minimum cementitious material content, CM content, the minimum amount of cementitious materials in concrete mixtures, including both traditional Portland cement and SCM. Other parameters include water-to-binder ratio, aggregate types, maximum aggregate size, or admixture usage. Here are some examples of prescriptive specifications of concrete mixture. This table lists the high-ranking prescriptive specifications. This is a minimum cementitious material requirement from Mass DOT and the SCM content requirement, which are different from different SCM types. These prescriptive specifications are designed to ensure the quality and durability of concrete products. However, they may have some limitations or negative impacts. First, they impose constraints on concrete mixtures and limit the flexibility in concrete production. For example, requiring a minimum cementitious material mass can lead to overdesign and resource inefficiency, as Soroush explained. Additionally, prescriptive specifications often restrict the use of low-carbon materials like flash and slag and lead to higher JJ emissions. For example, in this figure, if we remove these prescriptive specifications, it would enable significant JJ reductions, and we can find an alternative products instead of the low-carbon products within the constrained space. So it's widely recognized that concrete prescriptive specifications contribute to increased JJ emissions, but there is a notable lack of quantitative analysis to precisely measure this impact. Quantifying the JJ impacts is crucial. However, there are some difficulties in the quantification, such as the lack of comprehensive operational real-life data, the variations in specification types, and probably it will involve complex interactions between specification and the impacts. So it increases the difficulties in the quantification. Therefore, our objective is to evaluate the environmental impacts of prescriptive concrete mix specifications and the benefits of moving away from prescriptive specifications. We are quantifying the JJ impacts associated with prescriptive specifications, focusing on minimum CM content and maximum SCM content limitations. Identify potential JJ savings from relaxing these prescriptive specifications, and evaluate and compare these JJ savings across all US DOT specifications. So this research aims to quantify the JJ impact of concrete prescriptive specifications by exploring the relationship between concrete mix characteristics and JJ emissions within the context of state DOT specifications. So our approach developed a concrete spec-aware JJ predictive model. It's used to estimate JJ emissions associated with different specifications. Here is our spec-aware JJ model, considering CMS and SCM content to make predictions on JJ emissions. It can reach an accuracy of about 98%. The predictors are defined based on state DOT prescriptive specs, So we call it spec-aware model. Using the spec-aware model, we can analyze concrete products within the constraint space defined by the customer requirement. By inputting the constraint space into the model, we can evaluate all concrete products that meet these constraints and identify low concrete products within the constraint space. When we input the prescriptive specifications into the spec-aware model, it will calculate the associated JJ emissions, which we refer to as JJ benchmark. The JJ benchmark is the lowest JJ can be achieved when meeting the specs. Additionally, if we expand the analysis to include the entire feasible space of concrete products, the spec-aware model can help us identify alternative products with even lower JJ emissions. So in this study, we analyzed the MassDOT prescriptive specs from concrete product, as shown in these figures. There are some previous versions of MassDOT, and as far as I know, they updated some of their specs, but we will use these specs as this case study. So we investigate the JJ impacts of minimum CM specs and maximum SCM specs individually, and also the combined impact of both minimum CM specs and maximum SCM specs. This slide shows the results when minimum CM specs are applied. We did the analysis for all different design PSI, and here only shows the result for 3,000 and 4,000 PSI. This heat map represents the JJ saving compared to the JJ benchmark we identified, and the blank area represents the infeasible space for a certain design PSI. So the dashed line in this figure represents CM spec, and it's corresponding to the JJ benchmark, which will lead to 0 JJ savings. When the CM is lower than the CM spec, it leads to lower JJ emissions and positive JJ savings. And when CM is higher than the CM spec, it leads to higher JJ emissions and negative JJ savings. Generally, CM spec decreased by 10 kg per cubic yard will lead to 8 kg per cubic yard JJ reduction. And in this figure, the JJ reduction gradient is kind of horizontal, but CM spec is more costly for JJ when SCM is lower. We also investigate the actual JJ savings based on the operational data from ready-mix concrete mixtures. In these figures, the scatters are the concrete database we have. Based on the CM spec, we'll classify the concrete products into 2 groups, the relaxed group and the constrained group. We compared the JJ emissions between constrained and the relaxed group, and the average delta JJ is about 22 kg per cubic yard for 3,000 PSI concrete and 35 kg per cubic yard for 4,000 PSI concrete. This slide shows the results when maximum SCM specs are applied. And the SCM specs are defined by MassDOT, which requiring no more than 30% fly ash in concrete mixtures. Similarly, the heat map here represents the JJ savings compared to the JJ benchmark. The dashed lines are the SCM specs. They are representing the JJ benchmark, and it will lead to 0 JJ savings. When the SCM is higher than the SCM spec, it leads to lower JJ emissions and positive JJ savings. When SCM is lower than SCM spec, it leads to higher JJ emissions and negative JJ savings. Generally, when SCM content increases 10%, it leads to 25 kg per cubic yard JJ reduction. The reduction gradient is kind of vertical in this figure, but the SCM spec is more costly for JG when CMS is higher. We also investigated the actual JJ savings based on the operational data as shown in scatters here, and we classify the concrete products into constrained group and relaxed group based on the SCM specs. Then we compared the JJ emissions between the constrained and relaxed group. And the average ΔGG is about 29 kilogram per cubic yard for 3,000 PSI concrete and 39 kilogram per cubic yard for 4,000 design PSI concrete mixtures. At last, we applied the minimum CM specs and maximum SCM specs simultaneously. The dashed lines in this figure represent SCM specs and CM specs, and the crossover point is represents the GG benchmark. So the GG benchmark representing 0 GG savings, and the GG reduction gradient is about 45 degrees here. In this figure, a higher SCM content combined with a lower cementitious material mass will lead to lower GG emissions and significant GG savings, while a lower SCM content and a higher SCM mass will lead to higher GG emissions and negative GG savings. If we combine these two impacts, a 10 kilogram per cubic yard CM decrease combined with 10% SCM increase will lead to about 30 kilogram per cubic yard GG reduction. So here in this figure, we have the constrained and relaxed group, and within the relaxed group, we have the SCM relaxed group. They are concrete mixtures bounded by CM spec, but freed from SCM spec. We have CM relaxed group. They are concrete mixtures freed from CM spec, but bounded by SCM specs. And both relaxed group, the concrete mixtures freed from both CM and SCM spec. And we investigate the actual GG savings by comparing these four groups, the both constrained SCM relaxed, CM relaxed, and both relaxed group. When comparing the both constrained and the both relaxed group, the ΔGG is about 50 kilogram per cubic yard for 3,000 design PSI and 59 kilogram per cubic yard for 4,000 design PSI concrete mixtures. So in summary, concrete prescriptive specifications such as minimum CM and maximum SCM limit constrains the ability to produce low carbon concrete. Relaxing these specs can achieve substantial GG reductions. Actually, in addition to the analysis of one specific state, we are also trying to analyze the GG savings of all state DOTs and all combinations of CM and SCM limits. As shown in this figure, we developed 3 scenarios to analyze the ambitious, moderate, and conservative GG savings from the GG benchmark. Ambitious ΔGG represents scenarios that we totally remove specs, and moderate ΔGG represents scenarios that we partially relax the specs by 50%. And conservative ΔGG represents scenarios that we slightly relax specs by 25%. And based on the literature investigation, we found that all states and DC have prescriptive specs that increase GG emissions. 32 states and DC limit both CM and SCM. 6 states limit CM only, and 12 states limit SCM only. Among all states, we found Florida, RIND, may have the most flexible specs that allow lower GG reduction and allow lower GG reduction potential. Yeah, and ARKYSD shows the highest GG reduction potential through spec improvements because their current specs are more constrained. And at last, based on the transportation-related cement consumption, we mapped the GG savings per cubic yard to the total GG savings for each state at ambitious, moderate, and conservative scenarios. In this figure, you can see Texas and California show highest GG savings in this figure because they have more transportation-related cement consumption. But their specs are kind of normal. They are not too constrained or not too flexible. Yeah. In total, our analysis indicates that prescriptive specifications can cause up to 10 million tons of additional GG emissions at the ambitious level. Yeah. So considering the significant GG reduction potential, our recommendation is to like transfer from prescriptive specifications to the performance-based specifications. But for this objective, we should develop equivalent performance metrics and develop pilot and valid new approaches. Yeah, and that's it. That's my presentation. Thanks for listening.